You're feeling. We want to communicate not just through our repeater to the next county, but to the far corners of the world. We close our eyes and picture ourselves in a darkened room, sitting behind an old radio set. The radio gives off a glow that fills the room with its warmth, and from its speaker comes the sound of places never visited. Yes, we as hams are lucky to be able to feel that special feeling. And our technical expertise is what makes tonight's presentation by Paul so appropriate. Last summer, I attended a seminar given by the Society of Amateur Radio Astronomers at the National Radio Astronomy Observatory, or NRAO, in Green Bank, West Virginia. This has to be one of the most isolated spots on the East Coast. To get to Green Bank, you drive down I-83 for about 2 hours, then exit I-83 and head west into West Virginia. Now you're on secondary roads, heading over one mountain range after the other. After about 10 minutes, you notice that your cell phone has stopped working. After an hour, you notice that you can't pick up any radio stations on the FM broadcast band. And you also notice that you can't access any 2-meter repeaters. You are in the twilight zone. You continue to drive through this remote but beautiful rolling countryside for another hour and eventually see through the mist on the horizon, far in the distance, glowing in the late afternoon sun, several giant dish antennas pointed skyward. This is NRAO Green Bank. The NRAO is dedicated to the reception of radio signals from space. These signals are created by natural cataclysmic events occurring in the cosmos. Stars forming, galaxies colliding, neutron stars spinning on their axis at incredible rates, perhaps even black holes gulping in matter from around them. These natural events emit radio waves that enable scientists, radio astronomers, to study and better understand the universe. But perhaps buried in this crescendo of cosmic noise is something else. At this seminar in Green Bank, I attended Paul's presentation on the search for extraterrestrial intelligence, or SETI. I found it spellbinding. We strolled the grounds of NRAO afterwards, discussing a wide range of related subjects in the shadow of the giant radio telescopes. It was a fascinating 3 days. Dr. H. Paul Schuck, aerospace engineer. Did I get it right that time? All right. Is the professor of electronics at the Pennsylvania College of Technology. Paul is also the executive director of the Seti League, an organization dedicated to the microwave search for coherent signals from space. Paul is currently on a 2-year leave of absence to head the Seti League full-time. Paul received his PhD in engineering from the University of California, Berkeley. He has taught for more than 20 years and is the author of over 150 publications. He is credited with the design of the world's first commercial home satellite receiver. His honors include the National Space Club's Dr. Robert H. Goddard Scholarship, the Experimental Aircraft Association's Safety Achievement Award, a Hertz Foundation Fellowship in the Applied Physical Sciences, the Hertz Doctoral Thesis Prize, and the Central States VHF Society's John T. Chambers Memorial Award. Paul also serves as an FAA Aviation Safety Advisor, a fellowship interviewer for the Hertz Foundation, a manuscript reviewer for several journals, has been the advisor to the National Science Foundation, and is military program evaluator for the American Council on Education. I should also mention that Paul also holds his extra class amateur license under the call of N6TX and has chaired the UHF-VHF Advisory Committee of the ARRL. Paul served as technical director and board chairman of Project Oscar, the predecessor to AMSAT, and currently serves as director of the Central States VHF Society. Finally, Paul, I'm going to keep doing this to you. Finally, Paul is listed in a plethora of Who's Who's journals, including Who's Who in Aviation and Aerospace, Who's Who in California, Who's Who of American Inventors, Who's Who in Science and Engineering, and Who's Who in American Education, and many others. At this time, I would like to present Dr. H. Paul Schuck.
Well, thanks, Dick. Really great pleasure to be down in New York. Dick told you all how to get to Green Bank, West Virginia. I came here today from Williamsport, Pennsylvania, and I'm going to take a moment to tell you all how to get to Williamsport. Head up 83 until you get to U.S. Route 15. Turn north on 15 and go back 100 years. All right. This is the home galaxy, folks. 400 billion stars. About 10% of them, about 40 billion of those stars, are very much like our own sun. About 10% of those stars, about 4 billion, we now have reasonably strong evidence to suggest, have planets. About 10% of those planets, about, what is that, we're coming at 400 million now, are Earth-like. About 10% of those Earth-like planets, about 40 million, got to keep track of my zeros here, are life-bearing. About 10% of those life-bearing planets, about 4 million, have life forms that have developed what we would consider to be intelligence. About 10% of those intelligent civilizations, about 400,000, have developed technology. And about 10% of those technological civilizations, about 40,000, probably have radio communications. That's a lot of DX out there, waiting for us to work them. Today we're going to be talking about the amateur attempts to communicate with these other hams on planets orbiting other suns. We're going to talk about the amateur involvement in the search for extraterrestrial intelligence, SETI, and specifically a program that I've helped to generate, a program called Project Argus, named after the mythic Greek guard beast that had 100 eyes and could see in all directions at once. The Argus concept when fully implemented, will ultimately involve 5,000 radio amateurs around the world using small home-built radio telescopes to do something that neither NASA nor any other government agency has ever conceived, and that is to see in all directions at once, so that no direction of the sky should evade our gaze. This is the dream, and it's all predicated upon the assumption that there's life out there. Of course, we've been speculating forever. Here Nancy is asking, I wonder if there are people up there on Mars, and Sluggo is saying, of course not. And they're also speculating, as you've seen, Nansoid. Nansoid has just asked Sluggoid, who's responding, of course not. That works a little bit better. The studies which have led to the development of SETI are an outgrowth of a field known as radio astronomy. Unlike most scientific disciplines which have just evolved over eons, radio astronomy is a recent science. Its roots can be traced to a particular moment in history and a particular individual. And that moment was 1932, and that individual was Carl Jansky, the father of radio astronomy, the man who built this antenna at Crawford Hill, New Jersey, an antenna which has now been reconstructed at Green Bank, West Virginia, and Dick and I got a chance to see it last summer. A Bruce array antenna operating in the 15-meter ham band, built for one specific task, to find the source of QRN, natural interference, that was disrupting transatlantic radio-telephonic communications in the 1930s. Let me tell you about the proper way. Excuse me a second. Now, where is the cable? Missing something here. We have a rattle here, are we? Yeah, we got to bring that volume down just a little bit. Quite a bit of echo. Oh, that's right. I have been called a cross between Carl Sagan and Tom Lehrer. I do science like Lehrer and songs like Sagan. In the 30s, a phone call across the Atlantic would ride on a radio beam. And there would be bad interference and static, but only at times it would seem. At Bell Laboratories, a young engineer named Carl Jansky was given the task of solving the problem of static, and thankfully he knew the questions to ask. He built an array for the 20 meg region, so big it could not be ignored. To steer, it was turned on a circular track on the wheels of a Model T Ford. He discovered the noise was indeed periodic, but in an unusual way. The signals that Jansky detected appeared about 4 minutes early each day. The only conclusion that Jansky could draw was sufficient to boggle the mind. For the temporal pattern of radio noise, no terrestrial cause could he find. The static, he reasoned, must come from beyond, emanating from quite far away. We now know the sound was the song of the stars at the center of our Milky Way. Astronomy history, Jansky has taken a prominent place as he who
discovered the very existence of radio signals in space. We measure flux density these days in Janskys. They equal, you may be aware, just 10 to the negative 23 joules per second per Hertz meter squared. Well, of course, are we still on? Oh, maybe we had tweaked it far down there. Of course, whereas it took an engineer to discover the existence of cosmic static, it took a radio amateur to fully exploit it. And that radio amateur was W9GFZ, Grote Reber. Grote is the father of the radio telescope. He built the first parabolic dish radio telescope antenna in his backyard at Wheaton, Illinois, in 1937. It was quite a neighborhood eyesore, raised a lot of eyebrows. Today it has been reconstructed. Also, it has been moved to the National Radio Astronomy Observatory and exists to this day. Yes? This is a 10-meter or 30-foot diameter dish. And Grote built it out of regular hardware store materials available off the shelf. The size of the dish was determined by the length of the longest 2x4 he could buy in the local lumber yard. Dick and I also had the great opportunity, the great pleasure of meeting Grote last summer at NRIO Green Bank. He came down to do a seminar. Still controversial, well into his 80s, Grote gave a paper entitled "The Big Bang is Bunk," refuting all of modern cosmology. I'm not sure I believe him, but I certainly respect the man. A lot of amateur radio astronomy owes, in fact, all of radio astronomy owes its origin to Grote, but especially the idea that radio amateurs can make a contribution. Grote, you see, wrote a paper after he mapped the cosmos and tried to get it published in a scientific journal. And the problem was Grote's degree was in electrical engineering. What did he know about astronomy and physics? He had no formal training in those fields. Consequently, the Astrophysical Journal would not publish his article. Through an interesting quirk of fate, the article was finally published during the Second World War, when the editor of that journal had no submissions, because in those days all physicists in this country were working on nuclear weapons projects, and so nobody was writing any good physics articles for in the astrophysics field. The editor came across this old manuscript that had been sitting on his desk for years, having long been rejected, and figured, well, I can't publish an empty journal, I got to put something in it. So there we got Grote Reber's article finally in print. There's a lesson here for those of us who value education above knowledge. In Wheaton, Illinois, Grote Reber, he was quite a busy boy. When he built himself a dish about as big as you could wish, and he showed the world that it was not a toy. Reber's mother was a teacher, and Miss Grote on occasion taught a juvenile of note. One who never gave her trouble was the brilliant Eddie Hubble, and I know that was an influence on Grote. Reber pointed his antenna at the sky, and as countless constellations drifted by, he recorded in dB all the signals he could see, and became the first to map the Milky Way. He submitted his results for peer review to the Astrophysics Journal, though he knew that without a PhD they'd be skeptical, but he would be vindicated in a year or two. Every astrophysics expert had his say. They rejected Reber's radio Milky Way, for the signals he depicted very clearly contradicted every cosmologic theory of the day. Now Grote Reber, he was never one to mope, and he always could maintain a sense of hope. As the generations passed, he acquired an image vast as the father of the radio telescope. for the first 25 years of its existence as a discipline, radio astronomy concentrated on studying natural astrophysical phenomena in space. And then in 1959, a couple of scientists, a couple of teachers actually, who happened to be physicists up at Cornell University, New York, got this crazy idea that the same radio technology that was looking for signals of natural origin in space could also detect artificial signals. They knew about the existence of several interesting radio telescopes, including this lovely dish at Green Bank, the 85-foot diameter Howard Tittel telescope. And Giuseppe Cocconi and Philip Morrison wrote a very, very brief article in the British science magazine Nature, titled Searching for Interstellar Communication. Let me tell you what their colleagues thought of this silly notion. Phew, it would have been a lot easier if I brought a music stand along. Bear with me, please. Here we go. Crazy scholars of dubious stature, thinking they can converse with the stars. Dig their scandalous paper in Nature. Crazy Cocconi and Morrison are. Crazy, searching for communication. Tuning right on the hydrogen line. They say signals from alien nations reach us. They must be out of their minds. Drake is building equipment at Green Bank. Ozma, guess what he's planning to do? Listen to Epsilon Eridani at H1. I guess that he's crazy too. Think of the universe they envision. Planets abundant and teeming with life. Colleagues must view their work with derision. They're crazy for dreaming, crazy for scheming. I only hope they're right. Now, the Drake to whom I referred in that song, Frank Drake, was a young radio astronomer at Green Bank, who was actually the person who conducted the very first SETI search. It was Frank who coined the acronym SETI. Now, we all know that a SETI is an intelligent extraterrestrial walking up to you saying, "Take me to your leader." No, that's not it at all. SETI, of course, the acronym stands for Search for Extraterrestrial Intelligence. And as Frank Drake envisioned it, SETI would be the application of radio telescopes and sensitive microwave receivers to the process of looking through the cosmic background noise for signals which could not be created by nature, could not be explained by any natural occurring phenomenon which we know and understand. And from that same Howard Tittel radio telescope at Green Bank, Frank set up to do just that experiment. Oh, I'm sorry, that's not Frank. Oh, close enough. He's looking through his little optical refractor telescope there saying, just checking. Unbeknownst to Frank, unbeknownst to Cocconi and Morrison, as they were writing their pivotal article in 1959, Drake was setting up at Green Bank to do exactly the experiment that they had described in their article. And they didn't know each other. Even though Frank had gone to Cornell University, they were operating completely in ignorance of each other. Frank was operating in great secrecy because if you are a young, up-and-coming radio astronomer, you do not deliver the death knell to your own career by letting the world know that you're searching for little green men. This was just not respectable science at all. So Frank was keeping this very, very quiet and very secret until Cocconi and Morrison's article came out and spilled the beans, and he had to go public and say, well, in fact, yes, I'm doing that experiment right now. He spent a summer looking at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, both about 13 light years away, both stars very much like our own sun, both stars believed to have planets, and still believed to probably have planets, although we have not directly detected them yet. And he listened on one frequency, the same frequency which Cocconi and Morrison's article suggested would be a good place to look. The 21 centimeter wavelength, 1420 megahertz, the radiation frequency of natural interstellar hydrogen. You see, when you look out at the space between the stars, as this guy is doing, you see a black empty void. But in fact, the space between the stars is not empty. There is an abundance of matter out there, about 1 hydrogen atom per cubic centimeter of interstellar space. That's not a lot of hydrogen density, but there's a lot of cubic centimeters of space out there. And each of these little hydrogen atoms sends out a little chirp at 1420 megs, which we can hear, which you will hear tonight when I turn on a receiver in just a few moments. And at NRIO Green Bank, it was Drake who actually did the first experiment, didn't receive intelligent signals. Basically, it was a shakedown to prove the concepts and prove the equipment. He did get an interesting interfering signal, which turned out to be, well, I'll tell you about that one in a moment. After the conclusion of Project Ozma, as this search was called, Frank received a lot of publicity, got a lot of attention. Other scientists said, I want to be involved in this process. Among these other scientists were some of my mentors and colleagues and professors. Names that come to mind. Barney Oliver, Dr. Bernard M. Oliver. He was the vice president of engineering for Hewlett-Packard, also the president of the IEEE, the Institute of Electrical and Electronic Engineers. And Barney heard about Project Ozma and went down to Green Bank to visit. Sam Harris, W1FZJ, some of you knew Sam, chief engineer of Microwave Associates in Boston. He went down to Green Bank to participate. He actually built the parametric amplifier that Frank used right here at the focal point of that antenna. A young assistant professor from Berkeley named Carl Sagan was there. Melvin Calvin, the Nobel laureate from Berkeley, the biochemist. Some other legendary names. Of course, Phil Morrison got involved, having written the original article. And John Lilly, a psychologist who studied communicating with dolphins. His specialty was dolphin communications. He was there because he figured that this was another example of interspecies communications challenge, and they needed his guidance and assistance. A year after Project Ozma, Frank convened the world's first SETI conference. That's when the term was coined. In 1961, he convened a conference at Green Bank. For the agenda of that conference, he wrote actually an equation which purported to identify the 7 different factors that went into solving the problem of how many communicative civilizations there are in space. We'll go through the equation a little bit later, but suffice it to say right now, this is an elegant mathematical tool for quantifying our ignorance. Well, heck, let's let John Denver tell you the rest. antennas in the valley, Quiet Valley, Green Bank, West Virginia. You can slice the silence with a knife. Microwave receivers search for signs of life. Will the NRAO be the ones who will show all of mankind we have neighbors? Make it so. NRAO. Project Ozma, 1960. Frank Drake surveys two of our companions. When he hears a signal from the sky, spacecraft interference, not an ETI. Will the NRAO be the ones, come join me, who will show all of mankind we have neighbors? Make it so. Our destiny on 1420 megahertz, searching for intelligence from worlds far away. So far we have verified no alien transmissions, but we will any day. Soon the Order of the Dolphin makes this a respectable endeavor. Grand equation, courtesy of Frank. Glory to our SETI colleagues at Green Bank. May the NRAO be the ones who will show mankind we have neighbors. Make it so. NRAO. Make it so. NRAO. That Order of the Dolphin that I referred to was the name given to that first SETI conference, of course named in honor of John Lilly, the dolphin communications expert. The equation itself we'll come back to. From its auspicious beginnings in the 1960s, SETI entered a whole new phase, culminating in the publication in 1971 of this book titled Project Cyclops. You see, the summer of 1971, NASA actually got some funding together, actually money donated by the Institute of Aerospace Engineering, let's see, AIAA, American Institute of Aeronautical Engineering, to conduct a summer study workshop at Stanford University. And they pulled together 20 of the top minds in radio engineering in the country to spend 10 weeks designing on paper the ultimate radio telescope. What they designed was an array of 900 dishes, each 100 meters in diameter, which could be built for the paltry sum of 20 or maybe 50 or maybe $100 billion. They were a little shaky on the exact numbers. Cyclops, as it became known, was the greatest radio telescope never built. It did result in the publication of a wonderful engineering study. This book became the Bible for all radio telescope designers for a generation. I cut my teeth on the Cyclops report in 1971. NASA printed 10,000 copies, and they disappeared. They sold like hotcakes. The book had been out of print for 25 years Last year, my organization, the nonprofit membership-supported SETI League, working in collaboration with the old NASA SETI team, managed to get the rights to reprint, to republish the Cyclops report. This is a second printing, back in print for those of you who want to see serious engineering work. This is a guide to how to build a radio telescope on a $100 billion budget, and the SETI League has copies for significantly less, a $20 contribution. I should mention that we have another book that some of you took a look at earlier this evening. This is the SETI League's technical manual. This shows how to build a radio telescope on a $1,000 budget, somewhat more modest, and it only costs $10. So, copies available in the SETI store after we finish. The problem is, the whole Cyclops concept, which indeed did lead eventually to the building of the very large array in Socorro, New Mexico. They didn't build 900 dishes, they built 27 of them, but got to start somewhere, right? And this led to the impression that SETI is the sort of science which only governments can afford. And then, in the 80s, through into the 90s, that perception changed. Now it was believed SETI is a sort of science that not even governments could afford. You see, NASA did have a modestly funded SETI program for a few years. Operating out of a small office at the Ames Research Center in Mountain View, California, NASA SETI operated on a total budget of 5 cents per American per year. And they mapped out a 10-year project that would allow them to survey all 1,000 sun-like stars within 100 light years of Earth and search for planets and signals. NASA SETI went on the air with great fanfare on October 12th of 1992, the 500th anniversary of Columbus's first voyage of discovery. 1 year later, Congress pulled the plug. In October of 93, Congress, in its NASA research budget authorization bill, deleted 2 scientific programs. The multi-billion-dollar superconducting supercollider that was being built then at Waxahachie, Texas. And in the same legislation, they also terminated NASA SETI. They saved real money when they canceled the supercollider. When they canceled NASA SETI, they reduced the federal deficit by 0.0006%. What was their reasoning? Very simply, this stuff was too expensive. Senator Richard Bryan from Nevada said on the floors of our hallowed government halls, here we have been listening for a whole year, said Bryan, and not one little green man has come up to us and said, take me to your leader, which proves that this is a waste of money. 1 year out of a 10-year run. Well, this is one perception of SETI, the sort of science that only governments could afford and not even governments can afford. Let me show you the other perception of SETI. It's a sort of science that amateurs should be able to do with their typical microwave rover stations. Well, I think reality falls somewhere between the two extremes, and we're going to talk today about what it is that amateurs are doing to keep the search alive in the wake of Congress having not only terminated the current funding for NASA SETI, but here's the insidious part, passing legislation prohibiting NASA from ever again engaging in this type of research, on the grounds that NASA's job is to build rockets and go to planets and moons. Oh well, different perceptions there. The whole concept, this whole notion of amateur SETI with simple low-cost equipment is somewhat controversial. The giants in the SETI community have been unanimous in their skepticism. What, after all, can we, with our limited training and non-existent budgets, what can we possibly contribute to real science? And that skepticism was wonderfully articulated by my mentor, Dr. Bernard M. Oliver. You see, Barney Oliver, after he retired from Hewlett-Packard, became the head of the NASA SETI office until they were terminated. And Barney said, when we first started this idea of an amateur SETI, he said, if the best, most sensitive radio telescope which you can build is not capable of detecting even the strongest signal coming from even the nearest star, then thousands doing it or years spent in the effort will not improve your odds any. And then Barney went on to say something rather curious. He said, to cross the Golden Gate, we need a bridge about 10,000 feet long. 10,000 bridges, 1 foot won't hack it. Now, I cannot refute the logic. The reasoning is very, very valid if SETI is a serial process. But I contend that SETI may indeed be a parallel enterprise, in which case thousands of participants can indeed improve our odds. I am pleased to say that toward the end of his life, Barney did come around to our viewpoint and did, during the last year of his life, serve very ably on the technical advisory board of the Seti League. So I feel somewhat vindicated. But let's consider why we think we have a chance of success. The whole notion, the assumption that extrasolar planets exist in abundance. The numbers that I gave you at the beginning of the talk were my personal solution to the Drake equation. Remember, the bottom line was 40,000 other civilizations out there with whom we could communicate. That's within the Milky Way galaxy. Frank's estimates are a little bit more conservative than mine. Frank Drake himself says, no, it's 10,000. Well, astronomers say 10,000, 40,000, what's the difference? I wish I could deal with money like that. This whole notion of the existence of extrasolar planets was highly controversial. It was long assumed that certain types of stars should just naturally have planetary systems, but we had no evidence to support this. Throughout practically the entire history of astronomy until just October of 1995. And the reason we had no evidence is that stars typically outshine their planets about 1 billion to 1. And therefore, trying to see a planet orbiting a star is a little bit like trying to view a firefly perched on the rim of a searchlight. Since you can't do it optically, you have to adopt other techniques. One of the techniques that was used early on to search for planets was infrared astronomy. And the problem with infrared astronomy is it has to see through the Earth's atmosphere, and the Earth's atmosphere is pretty opaque at infrared frequencies. So we had to put a spacecraft into orbit. And that spacecraft, IRAS, like 20 years ago, brought back our first evidence that other planets might someday conceivably exist. Around the star Beta Pictoris is a thin, diffuse disk of dust and debris, which we now know to have been a protoplanetary system, the dust from which planets would later congeal. But this is not evidence of planets. This is merely evidence that the planetary formation process was going on. The first evidence of planets didn't come until much more recently. In 1992, radio astronomer Alex Walshton at Pennsylvania State University, using this antenna, the famous Arecibo, Alex detected a very, very interesting phenomenon. He was looking at a pulsar. A pulsar, you may know, is a rapidly rotating, very, very dense neutron star, which sends out very, very regular radio pulses. And studying this pulsar, Walshton detected what he thought was evidence of planets orbiting around it. I will come back to Walshton in just a minute because I want to tell you a little bit more about pulsars. Specifically, I want to tell you about Jocelyn Bell Burnell, the woman who discovered pulsars. At Cambridge, a grad student named Jocelyn Bell detected a signal, the tale I must tell. All regular pulses, the spectrum they span, to all indicate a little green man, and it's no, nay, never, no, nay, never, no more will I fall for a pulsar. No, never, no more. That's your part. The pulses were regular, quite strong enough, and in her report, Bell had labeled them scruff. She carefully studied and catalogued them, and these are the signals they called LGM, and it's no, nay, never, no, nay, never, no more will I fall for a pulsar. No, never, no more. Her research advisor, incredibly wise, who later would garner the great Nobel Prize, was Anthony Hewish, and he voiced some doubt. Don't publish until we can check this thing out, for it's no, nay, never, no, nay, never, no more will I fall for a pulsar? No, never, no more. She checked all her printouts, and Jocelyn could tell the computer had logged many others as well. Then Hewish said finally, I know what they are. A rapidly rotating dense neutron star, and it's no, never, no, nay, never, no more. Will I fall for a pulsar? No, never, no more. Their paper was published in Nature, of course, a rapidly pulsating radio source. Although Jocelyn and Tony preferred LGM, Frank Drake gave the moniker Pulsar to them, and it's no, nay, never, no, nay, never, no more. Will I fall for a pulsar? No, never, no more. To all SETI scientists searching for life, the message is clear: if you would avoid strife, check all of your data. Take care who you tell. Remember the pulsar and J.B. Burnell, for it's no, nay, never, no, nay, never, no more. Will I fall for a pulsar? No, never, no more. Well, the pulsars turned out not to be intelligently generated signals, but rather a natural phenomenon. However, a useful natural phenomenon. Getting back to Penn State and the Arecibo experiments, Alex Wolston about 5 years ago noticed that the pulses, the regular signals coming from one pulsar, were interrupted periodically. And he analyzed this periodic interruption of signals and figured out they were being blocked by 2 planets orbiting this pulsar. We now have strong evidence that other pulsars have planetary systems as well. These planets are not likely to be good life sites. A neutron star occurs when a star reaches the end of its useful life and collapses into itself, and the process of stellar implosion would have destroyed any life on the planets orbiting that star. Nevertheless, this is our first solid evidence that other planets might exist in the cosmos. Our first evidence, but certainly not our last. October 1995, at the Geneva Observatory, Michel Mayor and Dieter Hellos were looking out into space using a new instrument in the search for extrasolar planets. And what they discovered was rather startling. Orbiting the star 51 Pegasi, just 42 light years away, a companion object about half the mass of Jupiter, orbiting very, very close into the planetary surface with an orbital period of about 4.5 days. Now, the size of the planet is something of a selectivity criterion in action here. You see, the instrumentation that we use to detect planets is rather crude. Right now, we can only see the largest of planets. If you used our instrumentation that we have available on Earth, from 42 light years away, looking back at our solar system, you would see the Sun and Jupiter. Later, as our resolution improves, we'll be able to see Saturns and then maybe someday Earths. But right now, we can only see these giant planets. Nevertheless, the first confirmed extrasolar planet, announced on October 5th, 11 days later, Jeff Marcy and Paul Butler at the Lick Observatory in San Jose, California, independently confirmed the existence of the planet that's now known as 51 Pegasi b, the iron-nickel bowling ball orbiting near a sun-like star just 42 light years away. Oh, well, heck, let's illustrate it not with a star, but with me singing the same song to Michel Mayor, the discoverer, and his wife, Francois. They found a planet orbiting round Pegasus 51, a nearby yellow G2 star that's very like our sun. Astronomers, consider what your instruments have shown. It's just remotely possible that we are not alone. And could it be we're not alone at all? Let's be sure that we are listening when they call. If there's a planet orbiting a star that's like our sun, could there be life near Pegasus 51? In Florence, Michel Mayor of Geneva told the tale of careful Doppler measurements which hardly ever fail. The instruments he used are Horrivel and LOD. They clearly showed a planet that the eyes could never see. And could it be we're not alone at all? Let's make sure that we are listening when they call. If there's a planet orbiting a star that's like our sun, could there be life near Pegasus 51? The planet they've detected is roughly Jovian size. It didn't take the scientists too long to realize. It's not the kind of world that sentient beings would call home, but there could well be others, maybe one just like our own. And could it be we're not alone at all? Let's make sure that we are listening when they call. If there's a planet orbiting a star that's like our sun, could there be life near Pegasus 51? Now it starts getting technical, so take notes. The star that's known as HR 8729 is known to have a very weak Ca2 spectral line, just 40 light years distant of precisely solar mass, and temperature determined from its spectral type and class. And could it be we're not alone at all? Let's be sure that we are listening when they call. If there's a planet orbiting a star that's like our sun, could there be life near Pegasus 51? Now this is going to be on the midterm. The magnitude of 51 is 4.84. Our sun is 4.79, so who could ask for more? Its solar luminosity is 96%. 0.98 solar radii, a twin that's heaven sent. And could it be we're not alone at all? Let's make sure that we are listening when they call. If there's a planet orbiting a star that's like our sun, could there be life near Pegasus 51? The age of 51 is thought to be 8 billion years. Our sun is just 5 billion, but it definitely appears that 51 is far more rich in metals than our sun. That's not what you'd expect, so there is still work to be done. But could it be we're not alone at all? Let's make sure that we are listening when they call. If there's a planet or a star that's like our sun, could there be life near Pegasus 51? Throughout the local galaxy, a billion suns abound. We've long suspected planets, but this is the first one found around the solar system. But is there life? We cannot say. An active SETI program will determine that someday. And could it be we're not alone at all? Let's make sure that we are listening when they call. If there's a planet orbiting a star that's like our sun, there might be life near Pegasus 51. Well, now we're on a roll. From that auspicious beginning, we have now detected, according to this slide, 10 extrasolar planets around sun-like stars. That's as many planets around other suns as we knew about around our own. And just yesterday, I got an email, number 11 just came in. The Harvard Smithsonian Astrophysical Observatory just announced the detection of yet another extrasolar planet. They're all over the place. We have a graph here that shows, in terms of the distance from their sun along this axis and the mass of the planet along that axis, and they're scattered all over the place, some near, some far, some heavy, some light. The important part of this slide, though, is that we can identify a critical combination of mass and distance which would allow the planet to be potentially a good life site. You see, in these bands here, this region here, this is what's called the habitable zone. And if a planet falls within that range of distances from its star, it's got the possibility of liquid water. And if we have liquid water, we've got a really good chance for the development of life. We'll discuss the chemistry and the biology of that in a moment. But I want you to notice something here. Of these 10 planets that we've mapped out here, there's one clearly in the habitable zone and another one just on the edge of it. We have a couple of potential life sites already. Now, this planet in the habitable zone, 16 Cygni C, it's a warm planet. If it's got water, it's hot water. It's about 80 Celsius. That's quite a bit warmer than your hot tub. On the other hand, we do have some evidence to suggest that intelligent life can reproduce in hot tubs, so who knows? Now, I will admit that our emphasis upon liquid water is somewhat geocentric and somewhat chauvinistic. Not all life forms will be water-based. I mean, take this poor guy, for example. Here he is. His spacecraft has crashed in the desert, about 40 miles northwest of Roswell, New Mexico. And he's staggering along there. He's gasping, ammonia, ammonia. Well, it's true that all life does not have to be based on water. But if you look for the simplest way to produce life, we need a solvent. That's a given. You need to have a solvent. And it needs to be a polarized solvent. And water is the simplest polarized solvent in all chemistry. It's easy to create. It doesn't take a lot of energy to hold it together. And it should be abundantly available because water is made of hydrogen, which we know is abundant throughout interstellar space, and oxygen, which we also know to be abundantly available throughout interstellar space. The stuff is there. If we restrict ourselves to searching for water-based life, we will find a certain amount of life. If there are other life forms, that just makes the odds even better than we're assuming with our 40,000 numbers that I gave you a little earlier. Let's talk a little bit about the chemistry. Here's an experiment that was done by Melvin Calvin at the University of California, Berkeley in 1951. Dr. Calvin took a sphere, glass laboratory sphere, and he filled it full of the stuff of primordial atmospheres. Basically, hydrogen, carbon, and oxygen. And he added a spark of energy. Actually, he used a spark from the Berkeley cyclotron, but you could use electricity or, well, of course, lightning volcanism on planets provide the energy source. And over a period of just a few hours, inside the glassware, began to grow a thick, sticky, gooey substance, which was long-chain polymer organic molecules, life precursors. 2 years later, at the University of Chicago, Miller and Urey repeated this experiment. They added one additional element into their soup. They added nitrogen. And what they got out, folks, was amino acids, created in the laboratory from early planetary atmospheres and lightning. We can do it in the lab. Chances are the great designer could do it in the multiple labs around multiple stars. The chemistry of life is available, and it's commonplace throughout the cosmos. But does this mean that life existed? What's the spark that goes from amino acids to something that lives and breathes? Well, we don't exactly know. But we have some evidence to suggest that that spark has occurred. I'm talking about fossil evidence from meteorites. You all saw it in the newspapers, but in case you missed it, I'll show you the fossil evidence we found in meteors here. No, that's not right. I'm sorry, wrong one. Hans-Dieter Pflug in 1982 did an analysis of the Murchison meteorite, which has been found in Australia. And using scanning electron microscopy, he detected some very interesting structures inside the Murchison meteorite. And he said, hey, I know those shapes, I know those structures, those are fossilized bacteria. And he published this. And the jury was rather mixed. Sir Frederick Hoyle in England said, yep, looks like life to me. And Chandra Wickramasinghe, the co-author of Life Cloud, said, no, this is just prebiotic structures which mimic life. So the controversy was never resolved. Until this past August. August 96, NASA made some announcements about studies being done on this meteorite fragment, the Alice Hills meteorite, ALH 84001, which was found 1983 in Antarctica. And the Alice Hills meteorite, when analyzed under scanning electron microscope, also yielded some very interesting structures that are very much like the structures that Flug found in a different meteor sample seemed to suggest microbial life had existed. What really adds to the speculation about the Alice Hills meteorite is that it appears to have originated on Mars. We're not sure of that, but it seems that the chemistry in this meteor matches very closely to the chemistry of the soil samples that the Viking lander took on Mars. And if the meteorite came from Mars, we got a mechanism to explain how that could have happened because of a meteor impact, knocking ejecta off of Mars and it eventually reaching Earth. It's possible that this is a Martian artifact, but even if it's not, it looks like life from beyond Earth. It's controversial because the evidence is purely circumstantial. We have not yet seen their genetic structure, and until we do, we really can't be sure. But the evidence is promising enough that it was at least worth writing a song about. Within a Martian rock they found the fossilized remains of a microorganism that had neither brawn nor brains. We're gaining quite a glimpse into how life might have begun from the spot that's on the rock that's from the fourth rock from the sun. It's from a Martian meteor, and scholars think they know how it fell in the Antarctic 13,000 years ago. Though found in 1984, it languished till someone made a study of the rock that's from the fourth rock from the sun. Results are inconclusive, though it certainly appears that the fossils in the meteor date back 3 billion years. The scientific inquiry has only just begun of the spot that's on the rock that's from the fourth rock from the sun. With spectrographic readings and electron microscopes, they commenced to probe in ways that would rekindle Seti's hopes. Abundant PAHs could be found by anyone who would scrutinize the rock that's from the fourth rock from the sun. It's time to launch a mission to send robots back to Mars. Though it isn't inexpensive, it's much closer than the stars. If we could bring back samples, there is much which could be done to determine if there's life upon the fourth rock from the sun. Though others have disputed it, Sir Frederick Hoyle is fond of a theory that says life on Earth was seeded from beyond. And I'm the great-great-great-great-great-great-great-great-grandson of the spot that's on the rock that's from the fourth rock from the sun. Well, if we have life even at the microbial level, given enough life sites and enough time, it will evolve into increasingly complex organisms. Like these guys. They look like something from Stephen Jay Gould's book Wonderful Life, something that crawled out of the Burgess Shale. But in fact, this is the sort of life form that would happen next. Once you have microorganisms, it's not a very big step to more complex organisms, even organisms like this one in the middle that generate intelligence. Now, how do we know this guy is intelligent? Well, because he's discovered mathematics. Do you see that? Not only has he discovered mathematics, but if we take a close look, we'll see he has discovered the Drake equation. I'll go you one better than that. I have evidence to suggest that this guy is a graduate student. How do I know? There is an error in his equation. And I always leave it as an exercise to the students to find the error. Let's take a trip now to Ohio State University. Those of you who were here during the cocktail hour heard our little warm-up song about John Price, WHJK. John is one of the world's preeminent radio astronomers. At age 85, I think he is right now. He is still an active radio astronomer, and he designed and built the Big Ear Radio Telescope at Ohio State, the home of, This is confirmed by the Guinness Book of World Records, the home of the world's longest continually running SETI program. Ohio State Big Ear went on the air doing SETI in 1973. They will go off the air on August 15th of 1997. 24 continuous years of scanning for intelligent signals. The reason they'll go off the air is that the land has been sold out from under the telescope, and this is about to become a golf course and housing development, which is, of course, progress. I mentioned the Big Ear radio telescope at Ohio State because there have, in the 37 years since SETI was first founded, there have been about 40 different SETI searches conducted in various locations. And collectively, those searches have brought in about 36 candidate signals. That is to say, signals that have been received that appeared to fit the profile for what we would expect from signals leaking from the stars, from other intelligent civilizations. Not conclusive, not proof yet, but just tantalizing hints. Signals that could not be explained by any natural occurring phenomenon which we know and understand. The most spectacular of these candidate signals was received at Ohio State on August 15th, 1977, just 20 years ago. They were scanning the region just south of Sagittarius. If you're an astronomer, you know that Sagittarius is very near the center of the Milky Way galaxy. The galactic center is where there are the most stars. But they were looking in a region of Sagittarius where there aren't a lot of stars, and they detected a signal unlike any ever seen before or since. You probably know about it. This signal was mentioned even on the X-Files. People were so excited. The astronomer on duty, Jerry Eman, was so excited that when he looked at the raw data on the computer printout, he scribbled one word in the margin of the printout, and that word he scribbled gave the signal its name forever. And we're talking, of course, about the famous Ohio State University mom signal? Oh, yes, and when they decoded it, it said, "Eat all your broccoli. Children on Europa are starving." No, that's not right. I'm sorry. The wow signal. There we have it. You see, Jerry looked at the raw data, and he said wow, and he wrote wow. And I looked at the raw data, and I said, what? I don't know what this means, but fortunately I was able to feed that raw data into my computer. And when my computer graphed it, I looked at that, and I did say wow, because what do we see here? Well, along the horizontal axis, we have time. The vertical axis, that's your S meter, signal strength. And in the depth axis, we have frequency. This is a 50-channel receiver. We looked at a half a megahertz of spectrum in 10 kilohertz chunks. And here is a signal that existed on only one channel, a narrowband signal. Nature does not produce narrowband signals. Natural signals are hundreds of kilohertz wide. Here's a signal that was 10 kilohertz or narrower. Sounds like CW, or low-level modulation. And a signal that rose out of the noise and fell. The antenna was fixed. We're using the Earth as our antenna rotor. A signal that rose and fell in a pattern exactly consistent with the beam pattern of the dish, including the skew, because the feed was offset from center a little bit, including a little bit of asymmetrical skew, and side lobes over here and there, coma side lobes, which exactly fit the measured pattern of the antenna. And when you look at that signal, you can't help but say it looks clearly artificial. In fact, it looks artificial enough to be worth singing about. That might work. That's better. It was 15 August of 77 at the Big Ear Radio Telescope that a signal heard on the hydrogen line gave humanity cause for hope. Gave humanity cause for hope. Declination at minus 27. Right ascension, 19 hours and change. When the signal rose out of the noise, the astronomers knew it was something strange. Astronomers knew it was something strange. The The signal peaked at 30 sigma, 37 seconds at half power, in a single channel 10 kilohertz wide. The computer printout logged the hour. Computer printout logged the hour. The CPU analyzed the signal, strongest ever seen somehow. Jerry Eamon's eyes betrayed surprise as he wrote in the margin one word, wow. He wrote in the margin one word, wow. Was the wow a call from a distant planet? Sadly, we may never learn, though we looked again 100 times. The signal never did return. The wow signal never did return. That the wow came from an intelligent species never could be convincingly shown. Yet we still scan the skies with our radio eyes, because we know we are not alone. Because we know we are not alone. Now, why did the signal not repeat? Simple mathematics. The Big Ear radio telescope looks at a tiny piece of the sky at once. It's a huge beam with very, very narrow beam width. Huge antennas view small portions of the sky. In the case of Big Ear, 1/1,000,000th of the sky, 1 part in 10 to the 6th at a given time. And it's located on a rotating planet. That means that even if you have that antenna connected to a receiver that's on exactly the right frequency, that's turned on at exactly the right minute, when the call comes in, there is a 99.9999% chance you'll be pointed the wrong way. Now, but it gets worse than that, because let's assume for just a minute that this strong signal came from a distant star, from a similar antenna, on a rotating planet, illuminating 1/1,000,000th of the sky. Now, what are the odds that the two antennas are pointing at each other at the same time? And the statistician says, oh, that's an easy problem. 10 to the 6th squared, that's 1 part in 10 to the 12th. 1,000,000,000,000 to 1. And we've done 100 follow-on studies. Not only have we not scratched the surface, folks, we haven't even felt the itch. Well, we have, because we knew that this signal fit the profile exactly, in all respects, looked like exactly what we were looking for, we've tried very hard to repeat it, to duplicate it. Paul Horowitz, W1HFA at Harvard University, uses an 83-foot dish and the world's most sophisticated million-channel spectrum analyzer, and did several weeks of studies looking in the direction of the sky from which the signal emanated, and he heard nothing. 2 summers ago at the Green Bank National Radio Astronomy Observatory, I used a 40-foot dish and a very, very simple, low-tech, home-built, amateur single-channel receiver, that stuff over there, to look for the same signal. And I also heard nothing, proving that my equipment works just as well as Horowitz's. Now here's something puzzling. Here's a star map. Remember I said that there are an abundance of sun-like stars that have planets now that we know about? So here in the region of Sagittarius, in which the wow signal originated, we've plotted all the interesting sun-like stars. And we've overlaid on that the oval pattern, which is the beam pattern of the antenna when the signal was received. And from which of these stars did the signal originate? And the answer is none of them. You see, there's no stars inside the beam width of the antenna, at least no cataloged known sun-like stars. And this points up the danger of doing what we call a targeted search. Excuse me. The targeted search concept is a very popular way to do SETI. The first SETI study, Project Osmond, was a targeted search. You look with a high-gain antenna at a known star that's believed to be a good candidate. And we have a catalog of about 1,000 good candidates now. And indeed, we're looking systematically at those 1,000 stars. But for every star that we know about, there's a million others that we don't know about, that we don't have in a catalog. And the trouble with the targeted search with high gain, narrow beam antennas is we could be missing the interesting signals because we'll be pointing right next door and never hear the signals themselves. Ohio State is not doing a targeted search. Big Ear is doing what's called an all-sky survey. In the all-sky survey, you look preferentially in no particular direction. You just sweep out the whole sky day after day after day, systematically. It takes several years from Big Ear to see the whole sky. It's a very, very slow process. But you won't miss anything. Now, the two approaches are complementary, and SETI should include targeted searches as well as sky surveys. It turns out that targeted searches are best performed by the world's giant radio telescopes. The Big Ears and the Cyclopses and the Arecibos, those kinds of telescopes do a wonderful job tracking an individual star for hours on end with very, very high gain. But these huge telescopes are not very well suited to do the sky survey because they see too small a piece of the sky at once. So it seems that the ideal way to do a sky survey is to use smaller antennas that have wider beam widths and look at more sky at a given time. The problem is when you do that, you sacrifice sensitivity for sky coverage, and it's kind of a trade-off, and this is why you need both approaches. Now, what can we learn from the WOW signal? We don't know its nature. We don't know its origin. We believe it might have been incidental radiation from some other radio-using civilization, but we don't know that for sure. And after 20 years of follow-on studies, we are concluding that we'll probably never know that for sure. Or this might have been some previously undiscovered natural astrophysical phenomenon. That also is an exciting possibility. But we're just not going to know from this one sample. What we do know, however, is that we have a convenient benchmark here, because we can use the WOW signal as being representative of the sorts of signals we're looking for. We can use it to calibrate our thinking and use it to design our next generation of SETI equipment with this kind of signal in mind. And it is a benchmark that we, in amateur SETI, use the WOW signal for. I'll go through the number crunching very quickly since this is not a math class. We know a lot about the station at Ohio State 20 years ago when the signal was received. And from what we know about the antenna size, the capture area, the noise temperature, the bandwidth of the receiver, and how long they integrated, how long they collected photons, we know how strong that signal was falling on Earth. Its flux density was 4 times 10 to the minus 23rd watts per square meter, or about 400 Janskis, for those of you who think in Janskis. This is a known number. We now know how strong the signal was, how many photons per second fell on Earth, basically. We also, I'm sorry, I missed something here. Let me back up. We know that the sensitivity of the antenna was capable of detecting a 400 Janskis. We know that the signal itself had to be stronger than that because the signal was stronger than the background noise. So we now look at the sensitivity of the receiver, 4 times 10 to the minus 23 watts per square meter, or 400 Janskis. We look at that number, and we look at the signal-to-noise ratio, which is 14.9 dB, or S2.5, and we multiply the two together, and we see that the WOW signal was 1 times 10 to the minus 21st. Sorry for that figure there. Watts per square meter. We know how strong the signal was. Now, if we want to detect the next WOW signal that comes along, we better build a radio telescope whose sensitivity is better than this, who is at least capable of detecting 1 times 10 to the minus 21 watts per square meter. John Krauss says that just having the right equipment isn't enough. You've got to be doing the right experiment. And we now believe that the right experiment involves having a whole lot of antennas looking in all directions at once. Antennas capable of receiving at that level of sensitivity. Now, what are we going to use for antennas? Where are we going to get 5,000 radio telescope antennas? Well, my answer is from 5,000 backyards of 5,000 of my neighbors. You see, there's an awful lot of satellite TV dishes out there that make very nice little radio telescopes. Hams have been using them for bouncing signals off the moon for years. Why not use them for collecting signals from even farther away? So what we have done is design a typical radio telescope concept around an available backyard satellite dish. And your typical station, first off, the antenna diameter, 3 to 5 meters or so. Frequency range from the 1296 meg amateur band, tuning up through the hydrogen line, through the hydroxyl line, the interesting radio astronomy frequencies that happen to be in the quietest part of the radio spectrum, where the interstellar medium is most transparent. because that's the best place to look, is where you're going to have the strongest signals and the least signal attenuation. We know that we can keep the receiver noise down pretty low. We can keep the bandwidth pretty narrow by using computers to analyze our signal. You know, all know about digital signal processing in ham gear. That's what we use to narrow our receiver bandwidth from kilohertz down to hertz. And when we do so, integrating the signal for 10 seconds in a very, very expensive, high-tech analog to digital converter called a Sound Blaster card, using a home computer of 46 or higher, we can get about a 30 dB advantage. That's 5 S units of improvement just by using computer processing. So we put together a sample station, and our first one used an ICOM 7000 receiver, a really nice microwave scanner. Unfortunately, they're no longer being manufactured. ICOM has replaced it with the Model 8500. Great receiver, $2,000 price tag. Probably not practical for the amateur, but nevertheless, it was a way of showing the concept. Home satellite dish, ICOM receiver, Sound Blaster card, home computer, and we've got ourselves a station. And in fact, the actual first Project Argus station went on the air on Earth Day, April 21st last year. We had our grand ceremony to unveil it or to launch it. One radio telescope is interesting, but to survey the whole sky, we need a bunch of them. The actual number is 5,000. Where are we going to get 5,000 of these dishes? Fortunately, satellite TV programming is now being distributed through a new technology called DBS, Direct Broadcasting Satellite. And DBS service utilizes little tiny half-meter diameter dishes. And that means that there are tens of thousands or hundreds of thousands or even millions of 3, 4, and 5 meter dishes in people's backyards that are now technologically obsolete. And how lucky for us. What are you going to do with your old satellite dish, he asks? Boy, have we got a deal for you. Now, we're going to turn it into a radio telescope, and I recognize the big problem with amateur endeavors is we are not rocket scientists. So this is going to take a little bit of hand-holding. And that's where the Seti League comes in. The Seti League was founded in the wake of NASA's loss of funding. In the wake of Congress canceling NASA's SETI funding, the Seti League was formed by a group of radio amateurs, 4 radio amateurs, to help you to design, build, and operate small radio telescopes in a global project to detect the next wow signal that happens on our way. We are membership supported. We are a tax-deductible 501c3 organization, which means we do not receive any government funding, but we receive government favors. And the favor we receive from the government is that any money you contribute to us, they won't steal any of it. Let's take a look at just how sensitive our first Argus system was in 1996. Last April, 5 telescopes went on the air. 1 in Spain, 1 in England, 2 in the US, 1 in Canada. We're growing toward our goal of 5,000, slowly. Our first station, however, had a sensitivity, I'll skip the math and go right to the bottom line, 5 times 10 to the minus 22 watts per square meter. Is that good enough to hear the wow signal? Yeah. Would the wow signal be strong? No, it would be about S1/2. That was a pretty marginal system, but it would have detected the next wow. John Krause believes that these signals may be very strong but highly intermittent. He feels that we're looking for the small fish in the big pond and you need a huge net to catch it. And we're trying to stretch that net. When we threw the big switch to launch our first station, it was with the realization that we were going to need a whole lot more stations to become a meaningful endeavor. Let me show you the problem of all sky coverage. If you want to see in all directions at once with a real radio telescope, something of the 100-meter diameter variety, conservatively speaking, we're talking about a budget of $50 trillion. You see, you need 1 million of these telescopes, and at a conservative $50 million apiece, but I think it's more like 100 million, 200 million with the cost overruns that are inevitable, we'll very quickly exceed the gross planetary product. On the other hand, at the outside, a ham's going to spend $3,000 on his SETI station. Most of them do it for $500 or $1,000. Some of them buy everything off the shelf and don't build anything and spend $7,000, so it depends. But let's say a typical $3,000 station, I think that's being a little bit pessimistic. We can build the whole network of 5,000 telescopes for much less than the cost of 1 big ear. This is cheap science, folks. This is a bargain. And it's an even better bargain for the government because they don't have to foot the bill. You and I do when we build our own stations. Well, that first Argus station had marginal sensitivity, just barely able to detect a wow. But we weren't going to stop there. We figured we could improve things. And we did it by looking at some of our high-tech devices, like our very, very elegant waveguide feed horns on the antennas. We figured, well, if we just add a choke ring to the coffee can feed, we can improve the gain a little bit. And indeed, that's an easy change. The actual antenna's over there, and we'll take a look at it later. Same thing was true with our preamps. Our first low-noise amplifiers were very, very elegant microstrip technology built with what I call an approxo knife. There's nothing exact about it. And if we went to photolithographic etching techniques, we could certainly get our microstrips a little bit more precise and lower the noise of our receiver a bit. And I'll show you some of that hardware. And then, of course, we make better dishes and slightly bigger dishes. We also look at the idea of putting multiple feeds on our dish, so when we're not doing SETI, we can be watching TV on them. I mentioned the very expensive commercial scanning receivers, the ICOMs that we started off with. We decided early on that we're not going to get thousands of amateurs involved until we can get rid of that $2,000 receiver and go to something cheap. So we developed a homebrew converter that took the hydrogen line and converted it down to 2 meters, because everybody's got a 2-meter radio. And this converter is about to become available commercially as a $130 kit. Like that a whole lot better than buying a big expensive microwave scanning receiver. Once again, elegant technology here. You'll notice the approxo knife cuts all over the circuit board. Then, of course, you got to test your system in some way. You got to see, is it indeed working? And one way we test the system is we build ourselves some little crystal-controlled oscillator boards that put out a weak signal at 1420.40575 megahertz, the hydrogen resonant frequency. A simulated hydrogen source, just to test everything to see if it's working properly. Then we need software, and we've got members all over the world working on software. Dan Fox, I love his call, KF9ET, is the author of the Seti Fox program that most of our members are using. And Dan, in fact, was the recipient of the SETI's Annual Technical Achievement Award, the Bruno Memorial Award this year, for developing this wonderful piece of software, and also for detecting some interesting signals. So you would take the improved receivers, the down converters, the improved amplifiers, the better antenna feed, put it all together with a nice dish, and look at the sensitivity just a year into the run. As of right now, we've got our sensitivity up to 4 times 10 to the minus 23rd watts per square meter. I know you don't remember the numbers from the previous slide, so I'll give you a comparison here. The wow signal was 10 to the minus 21. Big ear could hear down to 10 to the minus 23rd. Argus 1 was in between, 10 to the minus 22nd. But Argus 2, the second generation, a year later, is exactly the same as the sensitivity of Ohio State Big Ear 20 years ago. Conclusion, the amateur state-of-the-art lags behind the best that science can do by about 20 years. We have caught up to Ohio State. Well, not really, because you see, in these 20 years, they have employed the same advantages that we employ, so they're even better now, except for one detail. They're going off the air in 4 months, and we'll still be there. Now, this number here, this is an important number, 10 to the minus 23rd watts per square meter. It was the sensitivity of Big Ear 20 years ago. It is the sensitivity of amateur SETI today. And it is the sensitivity that NASA said 20 years ago was needed and possible to do SETI. Phil Morrison wrote this statement in a NASA manual in 1977. He said in a few years we'll be able to do 10 to the minus 23rd watts per square meter. Well, guess what? He's right. We're doing it right now. Thank you, Phil. One of the challenges when doing amateur SETI, however, is maintaining our scientific credibility. The last thing we need is a hoax like this one. He's saying, boy, I wish I could be there when they discover this one. Our search went on the air April 21st of last year. On May 10th, just 3 weeks into the search, we got our first wow, our first hit. And there it is. Here we have a spectrograph that shows frequency horizontally, time vertically, amplitude is shown in the colors. And here's a slowly Doppler shifting signal. Fairly weak signal, clearly evident. 2 hams in England received this signal 3 weeks into the search. We learned several things from this hit. First of all, I looked at the signal, they looked at the signal, the computer software looked at the signal, we said something's wrong here. This slope is not right. This signal is not emanating from the stars. Neither is it emanating from Earth. It's coming from somewhere in between. And the way we know this is we know the rate at which our Earth rotates. You know that relative motion between a transmitter and receiver causes a frequency shift, the Doppler shift. You can do this experiment very easily. Stand on the railroad track, listen to the whistle on the approaching train. Now, if you're able to, listen to the whistle on the receding train. It's a different pitch, isn't it? Well, we know we can easily measure the Doppler shift on a signal. The computer can do that for us. Not only that, we can easily calculate what the Doppler shift should be for a signal emanating from the stars. If a signal is terrestrial interference, if the transmitter is on Earth and the receiver is on Earth, as Earth rotates, there's no Doppler shift. So a signal without Doppler shift is terrestrial interference, and we can tell the computer to ignore that. If the signal is coming from a very, very rapidly moving aircraft or spacecraft that moves across horizon to horizon in 7 minutes, like the space shuttle, the Doppler shift is very high, and we can say, oh, that's too close to the Earth. We can ignore that one because the Doppler is too high. And in between, there's a critical Doppler, a critical rate of frequency change that fits the signature of deep space. And that's what we programmed the computers to look for. This first hit did not fit the profile. I had a hunch as to what it might be. Ken and Trevor sent me the picture over the internet, and I looked at it and analyzed the data file, the wave file, and said, oh, this looks to me like a low Earth orbiting satellite. And they said, yeah, but it was on, they told me the frequency, and they said, there's no satellites on that frequency. I said, yeah, I know, that bothers me too. Last summer I took this image to Green Bank, showed it to a room full of radio astronomers, one of whom said, oh yeah, I know that signal, we see it all the time, it's a classified Navy satellite. So much for having received a wow. But this was good news for 3 reasons. One, it's an extremely weak signal. The fact that these 2 hams in England could receive it at all on their home-built 3.5-meter dish speaks very well to their sensitivity. 2, we were able, from the Doppler characteristic, to identify it as being a low Earth orbit satellite. The software is working. 3, and most important, here are 2 hams who exhibited great restraint and showed wonderful discipline. They got the hit. They did not call the Times of London or BBC and say, E.T. is talking to me. Nope, they called Seti League headquarters and said, we got something here, can you have one of the other members verify it? That's the kind of thing that will give us scientific credibility, is working together as a community of amateurs to verify our findings. Just as happens in the optical astronomy community. Just like Tom Bopp and Alan Hale did, both independently identifying the same comet, sending in their email to the same clearinghouse which verified their findings. This is why the comet has 2 names. So will the next WOW signal, I suspect. There's another signal. I'd like to say that was E.T. calling home, but no, we know exactly what that was. The professional NASA SETI community, for years, used a test beacon, a signal generator in the sky to test their systems. And that signal generator was called the Pioneer 10 spacecraft. See, the Pioneer 10 carried a 5-watt transmitter, which operates from a radioisotope thermal generator. That's a nuclear battery, which means that it will continue transmitting for several plutonium half-lives, and that's a long time. And the Pioneer 10 satellite is now outside of the solar system, well beyond the orbit of Pluto, and yet NASA SETI, with its giant antennas, can still receive its beacon signal today. This is not the Pioneer 10 signal. We can't receive it. It's too weak for amateur SETI. It's too far away. But NASA very kindly last year launched another test beacon just for us hams, and it's called the Mars Global Surveyor Satellite. And it has a 1.3-watt beacon. That's this kind of power, folks. Omnidirectional antenna, 1.3-watt beacon on 435 megahertz, which is a ham band. And guess what? They turned the beacon on for us, hams, last November 10th, when the spacecraft was 5 million kilometers from Earth, and our software saw it and tracked it and measured its Doppler shift very easily. 12 hams in the SETI League received the Mars Global Surveyor at a distance of 5 million kilometers from Earth. Later this year, when Mars Global Surveyor lands on Mars, we're going to have a beacon on the surface of Mars, visible to us 12 hours a day from anywhere in the world. Wonderful opportunity to verify the operation of our systems, a weak signal source planted on Mars for our use. Thank you, NASA. One more signal. This one's something of a mystery. Dan Fox, the same guy who wrote the Seti Fox program, pointed his dish toward the Crab Nebula. Crab Nebula is a fragment of a supernova, star that exploded back 900 years ago or so. And we know that toward the center of the Crab Nebula is a pulsar. And that pulsar puts out interesting signals, and Dan wanted to look at the Crab Nebula pulsar signals with his SETI receiver. This is not the pulsar. Dan got that, but he also got something else unexpected. See, pulsar is a broadband signal. This is frequency horizontally. The pulsar would look all over there. But he got also a narrowband signal that peaked here, kind of in the middle of his frequency spectrum, a narrowband coherent signal on the hydrogen line. This is the first real amateur wow, because we still don't know what it is. And because it occurred early in our search, we didn't have enough stations online to verify it. We still have not confirmed this signal. It's a mystery. It tells us there are unexplained phenomena out there. There are things that we do not understand. There are things that we need yet to learn about. And those things can be detected by a group of maybe 5,000 radio amateurs working together as a team. My satellite antenna is pointed at the sky, but I'm not watching television, let me tell you why. I'm searching for existence proof of any alien race by sifting through the microwaves that fall from outer space. I am part of the search that's known as SETI. I'm a believer with a good receiver. There are coherent signals beaming at me, and when I find one, then I'll say, wow. Because the Drake equation says that N is roughly L. I'm praying that the aliens are all alive and well. By tuning through the water hole, I'm sure to hear them call. And when they do, we'll finally know we're not alone at all. I am part of the search that's known as SETI. I'm a believer with a good receiver. There are coherent signals beaming at me. And when I find one, then I'll say, wow. 5,000 loyal amateurs working as a team are making a reality of what was once a dream. If we are to be successful, then I have a single wish. Won't you please join the SETI League and build yourself a dish? Be a part of the search that's known as SETI. Be a believer, get a good receiver. There are coherent signals beaming at us, and when we find one, we'll all say, wow. It's gonna happen any decade now. This and 18 other songs are available in Sing a Song of SETI, the official songbook of the SETI League, yours for a $10 tax-deductible contribution. Now, that good receiver that you're going to get in block diagram form looks something like that. Don't be intimidated, they're only blocks. Only mixers and amplifiers and filters and all the stuff we always use. Hey, let me show you. Here, I don't need the mic for this. Waveguide feed horn with a choke ring around it. Imagine this at the apex of your satellite dish. Low noise preamplifier right on the feed horn so you don't have to worry about coax cable loss. Cable into our little homebrew microwave converter kit that shifts 1420 megs down to 2 meters. And let's see, little IC202 2-meter sideband radio. The biggest part of the whole system is the power supply. Okay, power on, receiver on, we have noise. Weak signal source. We have signal.
Wow.
We have Doppler shift. Hear the Doppler? Let the computer analyze that, folks. The hardware will be here for you to look at when we're done. It's low-tech. It's easy stuff. Our current initiative, the SETI League is currently working on our next generation high-technology receiver initiative, which was initially named STAR-1, S-T-A-R, for Spectral and Temporal Analysis Receiver. In part due to the sad news that we received just a few months ago of the death of our colleague, Dr. Sagan, we've renamed our STAR-1 receiver. We're calling it Mini-Meta, M-E-T-A. M-E-T-A was the name of Paul Horowitz's receiver at Harvard. It stood for Million Channel Extraterrestrial Assay. And Meta was named by Carl. Using Dan Golden's dictum of smaller, cheaper, better, we're now building Mini-Meta in Carl's memory. I'd like you to join me in a remembrance of our departed colleague here. Who is the colleague we won't... Oh, wait, before I get into that, let me teach you your part. I want you to work with me on this one, folks. The chorus is pretty easy. Now, go ahead and pick up your wine glass there and join me in this. This is what you're going to have to learn. Hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. His is a message that's bound to last. Billions and billions of years. Can you remember that part? Let's try it. All hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. His is a message that's bound to last. Billions and billions of years. Nice. Who is the colleague we won't forget, up to whom everyone looks? Wait a minute. That's, I had to change a line or two. Here he is. The colleague we won't forget, up to whom everyone looks. No, that's the wrong one too. Ah, here we go. This thing keeps getting changed. Consider it the ham process in action. Who is the colleague we won't forget? Someone the populace knows. It's Cosmic Carl on the TV set. Billions and billions of shows. So hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. His is a message that's bound to last. Billions and billions of years. Here's the word I was looking for before. Who was the author of great repute, up to whom everyone looks? Cosmic Carl's written without dispute billions and billions of books. So hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. It is a message that's bound to last. Billions and billions of years. Who knew genetics and told us so? Mammals and fishes and birds. Hear Cosmic Carl on the radio, billions and billions of words. So hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. His is a message that's bound to last. Billions and billions of years. In these austere and uncertain days, funding takes far more than luck. Who else except Cosmic Carl could raise billions and billions of bucks? So hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. His is a message that's bound to last. Billions and billions of years. 2 hit recordings for Voyager, bound for the planets past Mars. Cosmic Carl's own golden records are now heading out for the stars. So hail, Cosmic Carl, let us raise a glass. Billions and billions of cheers. His days is a message that's bound to last. Billions and billions of billions and billions of billions and billions of years. So what can you do? If you have World Wide Web access, please do check out SETI League's website, www.setileague.org, for over 700 documents totaling more than 20 megabytes of information. That'll keep you browsing for a few days. We do welcome radio amateurs as members. Memberships will be sold at the SETI store as soon as it opens after the talk. And if you don't have your checkbook with you today, you can fax us or phone us a credit card number or mail it on in. We'll have the application forms for you. Or email to join@setileague.org. Email your postal address if you don't have other access, and the proper forms will be mailed to you. And then, of course, as our toll-free number, our membership hotline, 1-800-TAU-SETI. That's TAU-SETI. Search for extraterrestrial intelligence. Or you can support us by helping us to do what nonprofit organizations have always done to stay in business, by buying a copy of the Cyclops Report or the Tech Manual or the Songbook or a T-shirt or a coffee cup or a mouse pad, or don't forget the important coveted SETI League pocket protector. Yes, you too can be a SETI nerd for a small contribution. Let's see. I lost my last slide. How can this be? I can't finish the talk without my last slide. Terrible. Excuse me. Here we go. Oh, okay. I feel better now. I had to have this one up here. In the vast universe are tens of thousands of other inhabited worlds that contain intelligences capable of electromagnetic communication. You may ask yourself, why have they not visited us? Maybe some of you think they have. I suggest that space travel is too expensive for them, and just as our government isn't funding it, neither is theirs. The distances between the stars are so vast that it takes a very long time and a tremendous amount of energy to send tons of metal hurling across the interstellar gulf. Fortunately, we can explore space without having to go there. We have something ever so much smaller and lighter and cheaper. The photon, the fastest spaceship known to man. And who better than radio amateurs to harness the photon? With it, we can gain the existence proof we seek. We can answer the fundamental question which has haunted humankind since first we learned that the points of light in the night sky are other suns. Are we alone? You will help me to find that answer. Thank you.
One question.
We have a question, yes.
Are you trying frequency for people to receive, or are you willing to do it, you got always the 6% and why are you going to do that?
Okay, the question was, how are we going to handle the frequency dimension, the frequency domain? Today, with only 27 or 28 active stations, coordination is kind of moot. We're in the shakedown phase. We're just developing the technology. So it's pretty much a free-for-all. Go look anywhere you want, on any frequency, in any direction. Just please document so that if you hear something, you can tell us what it is. Once we've achieved critical mass, and that'll come along about 1,000 stations or so, we'll have to start coordinating. The internet makes that coordination possible, incidentally. This would not have been possible 10 years ago. The plan is ultimately to assign coordinates so that we have the whole sky covered spatially. That covers a spatial variable, but there is still the frequency dimension to deal with. Right now, A 2-meter receiver driving a Sound Blaster card can look at a small chunk of spectrum at a time. About 12.5 kilohertz of audio passband is all we can process at once. That's today, and we are computer limited. Fortunately, being computer limited is a very good place to be because computers just keep getting better and faster and cheaper. Over the last 30 years, computer power has roughly doubled every single year. Now, extrapolation is dangerous. This is speculative. But if we are fortunate enough to be able to see computer power continue to improve at this same rate, then 10 years from now, our computers will be 1,000 times as powerful as they are today. And instead of being able to scan 12.5 kilohertz, we'll be able to scan 12.5 megahertz. And it's just going to keep getting better. Our receivers will be able to process more and more and more bandwidth simultaneously so that someday in real time, 20 years from now, we're going to be able to look at the whole microwave spectrum at once. Right now, all we can do is pick interesting frequencies, magic frequencies, and hope we get lucky. Soon, it won't matter because our receivers will be taking in the whole spectrum at one time. This technological development is coming about through the efforts of hams such as yourselves, and I thank you for your efforts. Yes, sir. Question.
Two questions. Why do you think a sunset signal will be found in microwave frequency spectrum? The second question, has there only been one sunset signal?
Let me answer the second question first. Was there only one WOW signal? No, there have been about almost 40 interesting signals detected so far. The WOW was the most dramatic of them. Paul Horowitz at Harvard University, in collaboration with our late colleague Dr. Carl Sagan, did a survey in which they detected about 30 interesting hits, 30 good candidate signals, when measuring from the Arecibo Observatory in Puerto Rico. Those 30 signals had something very interesting in common. They looked at the whole sky, but those 30 signals were all concentrated in the galactic plane. Now, if they were random noise, they would have come from all directions. That's pretty encouraging. But we need to do a lot more analysis. We need to have multiple stations verifying the signals simultaneously before we can draw any conclusions. But the fact that we've had over 3 dozen hits so far indicates that we're at least going about this process in the right way. Now, why the microwave spectrum? Several reasons. First of all, we have to base our search upon our own technological maturity. Right now, Earth technology is very adept at receiving microwave signals almost at nature's limit. We have microwave receivers that are very, very close to perfect. Receivers in other areas of the spectrum aren't quite so good, so we have a mature microwave industry. We have the capability. That's number one. Number two, interstellar space is relatively transparent at only a few ranges of the spectrum. Microwave happens to be one of them. Signals travel very well between the stars, relatively unattenuated at microwave frequencies. Other frequencies are blocked. Planetary atmospheres, same thing. Microwave signals shoot right through the atmosphere and the ionosphere quite easily. Lower frequencies get blocked by the ionosphere. Higher frequencies get blocked by the atmosphere. So we got this middle range that works very well when shooting through an atmosphere. And we speculate that if we have an atmosphere, obviously they do also to contend with. So they know this as well. Then again, the other thing is, we have exploited microwave technology on Earth for our own internal domestic purposes. I told you that stars outshine their planets 1 billion to 1, and that's true. But at certain times, on certain microwave frequencies, the Earth outshines the sun 1 million to 1. That sphere of microwave radiation is now all around our planet out to a distance of about 50 light years. Within 50 light years are 100 sun-like stars with planets. That's an estimate. If there are civilizations on some of those planets around some of those 100 stars, out to 50 light years, if they have radio astronomy, they already know that there's something artificial coming from our planet. Similarly, their leakage radiation will be detectable to us. If they're polluting their RF environment as effectively as we are, we would be able to detect their leakage as well in the microwave spectrum. Microwave is not the only place we're doing SETI. We have a lot of interest in optical SETI, looking for lasers, for example. Our sensitivity of laser receiving equipment is about 1 million times lower than our sensitivity of microwave receivers right now. Maybe in a few decades, that will become fruitful as well. Right now, if we want to maximize our chances of success, we have to go where our technology is most advanced, and in regions of the spectrum where other similar civilizations are also likely to have reasonably advanced technology. It's a guess, to be sure, but we got to start somewhere. Great question. Thank you. One more. Yes.
One other question. Are you familiar with the way optical devices
Oh yes, and the question is, am I expecting improvement in the optical industry? Absolutely, every bit as dramatic as the computer industry. And how is it going to happen? Oh gee, if I could answer that, I'd be investing in the stock market, in NASDAQ. The answer is, we are going to be developing higher power lasers. We're going to be developing more stable optical local oscillators and more efficient mixers for doing heterodyne optical receivers. I also believe we're going to get outside of the Earth's atmosphere with some pretty good optics in the near future, and that's going to make optical SETI all that much more practical. The SETI League recently announced an affiliation with the Artemis Society International. Artemis is one of the space privatization organizations that is trying to go to the moon commercially. And we have, as of a month ago, a pledge from the board of directors of the Artemis Society that when they have their first mission to the moon, they will carry a SETI payload if we design it. See, the Earth's environment is pretty polluted with all our communication satellites and navigation satellites. But if we get onto the far side of the moon, away from all the Earth's QRM, we have a much better chance of success. This is, we're talking 20, maybe 30 years downstream, but we've got to start planning this mission now, and the SETI League will be involved. We've been waiting since 1973 for NASA to take us back to the moon, and folks, it just ain't happening. If NASA can't get us back there, maybe Artemis can. Artemis will also be carrying optical SETI devices to get away from the problems associated with the Earth's atmosphere. Optical SETI will continue to be a better bet as our technology advances. Was there a question over on this side? Yes, sir. Polarization. Right now, this feed horn is linearly polarized. It's very easy to make a circularly polarized feed horn. Instead of one probe, you have two at right angles, and you use a hybrid coupler. And yeah, actually, you can put two preamps and two receivers on it and receive right-hand circular and left-hand circular. That's the next step. We haven't done it yet, but it's a step. And a good suggestion to that, but thank you. Anything else? Dick, the program is yours. Please visit.
Don't go anywhere quite yet. I'd like to present you with this. It's an honorary membership to our club.
Oh, my.
With all the privileges afforded to existing members, but I don't really know what privileges we have. But you will be getting our newsletter, and we again thank you very, very much for gracing us with your talk and your knowledge.
Thank you, sir.
Thank you very much.
That's nice.
score in the January VHF contest?
I say, folks, 2 years ago, since I came on board with SETI, I have not been on the air. I am receiving, but I'm not counting.
It's only a hobby.
Oh, heck, I might as well spill the beans.
That's right, it's only a hobby.
Well, says you it's only a hobby. Let me tell you something, folks. This is a scoop for those reporters who are here beating down our doors. Many of you are aware that I am officially right now in my second year of a one-year sabbatical from the Pennsylvania State University system. Don't ask me how I worked that. I got very lucky. And I'm at a kind of a career crossroads. At the March 22nd annual meeting, the Seti League Board of Trustees offered me a 5-year contract to stay on as its full-time executive director. This was not an easy decision because one does not give up a tenured full professorship lightly, but this was too good a deal to pass up. I have, as of last week, submitted my resignation to the Pennsylvania College of Technology. Effective August 15th, I will be a full-time Seti director for the next 5 years, so maybe it isn't only a hobby anymore, and I don't know if I'll ever get back on the air.
You hired one smart boy here tonight, I'll tell you. He did real well.
I said it before, he was spellbinding, and I hope you all felt the same way. One more hand for Paul. Well, that pretty much concludes our program for tonight. I thank everybody for coming. Hope everybody enjoyed it, and we're going to try and do this at least once a year. Good night, everybody.
Okay.
But I'm the president. I can do it. Being president's good.
You can apologize at the next meeting. You can apologize to everybody.
Just sit down.
Hey, your address is?
199 Maple Lane.